Good morning, class. Good morning, Shannon. If we don't finish this today, it's your homework, okay? Because tomorrow I'm recording. Because tomorrow we'll be looking at something else. Wanji? Because I'm using them to record. Because I got AirPods. Know what I'm saying? AirPods. Okay. Let's talk about geometric distributions. Now, like I told you before, all of these distributions are just fancy ways that mathematicians who studied these things before, the patterns that they found, and then they named them things, right? So remember, in a binomial distribution, what were some characteristics of a binomial distribution? Yes, independent trials. Any other characteristic? The probabilities are independent. Yes, there has to be a fixed number of trials. Mm-hmm. There's a probability of a failure and a success. And independent. Yeah, there are three. Now, for a geometric distribution, it's a kind of distribution in which you still have only two, you actually have one outcome that you're interested in, and you keep repeating the same process. Let me show you the thing. You keep repeating that process until you get the outcome that you want. What is it? Until you get the outcome that you are interested in. So think of a scenario in which I am throwing spatulas at Lynn, right? I'm trying to land the spatula on top of Lynn's head, right? So I'll keep throwing and throwing and throwing, and when I land the thing on Lynn's head, I stop because I have found the probability of success finally. It doesn't matter how many trials it takes. I will keep going until I reach that outcome. I think the example that's used here is if you're throwing a dart at a target, then you keep throwing the dart until you hit that target. If you don't hit the target, you do not stop, right? The probabilities in this case are also still independent. I mean, the trials are still independent of each other. So you can fill out those missing things on your worksheet. Please fill out those blanks using what you see.
It's time.
Why are you always doing a quiz in class, in statistics class?
Not to me. It's tough.
All right, so there are one or more trials with all failures except the last one. So until you get the one that you want, all of the previous trials are failures. So you keep repeating what you're doing until the first success, then you stop. In theory, the number of trials can go on forever. There must be at least one trial. The probability of a success and the probability of a failure for each trial is P plus Q is equal to 1, which means Q is 1 minus P, where X is the number of independent trials. Let's look at an example. Too fast? Too fast. It's fine.
So what are the rules for this?
The rules
Does
for
it have a fixed number of trials?
yes.
And then?
Still probabilities are independent,
Yeah.
right? And you keep going until you the success is your last trial.
Okay. So then no fixed number of trials?
No. The success is your last trial, and every trial before that is a failure.
So this is only about success, not failure. If you like succeeding, but you want to fail, you can succeed and succeed.
Yes.
Well, like if you're trying to aim that on Lynn's head and you want to, but you don't, like flip it.
Oh, if you're interested in the chance that you don't hit Lynn's head, yeah, then that could even just be one because then the
Because every time you failure would be until you get the success.
she said if you flip it, so if I flip this experiment, then the success will be not hitting your head.
Yeah.
Yeah. You want me to try?
Every time you go,
Yeah. Yeah. What's what she said.
That's not what she's saying.
That's what she's saying.
She said success will be that equal regret.
That's what I said. But then she said, what if you flip the experiment?
That's not what she meant.
What did she mean?
What she just said is different from what you're talking about.
No, I think, like, all here is about success, like, aiming what lives ahead.
Mm-hmm.
But then what if you flip it, like, what if every time you cross it, it's landing, and it's aiming? That's not possible, right?
Well, how do you know?
No, every time you flip it and it lands, then the experiment stops with the geometric distribution.
That's what she was saying, that if you flip the experiment and instead your success becomes not hitting Lynn's head. Yeah, that's what she was saying. So if you have someone that's a really good thrower and every time they throw it lands, then in that case the success can be not landing.
Mr. Williams.
Yeah. Just
So
semantics.
when you throw it to her,
Mm-hmm.
if it lands, that's when you stop.
Yes. That's when you stop because that will be a success. It doesn't matter how many trials it takes. Let's look at this example. You play a game of chance that you can either win or lose. There are no other possibilities. Oh, question. Your probability of losing is 0.57. What's the probability that it takes 5 games until you lose? What's that? What's the 1, 2, 3, 4, 5? The x value? I was reading the question. Okay. What values does x take on? Really? What values does x take on? Remember, what are some of the characteristics of a geometric distribution? Various or unlimited, right? So the values that it could take on are its unlimited number of trials. Yes. Yes. Yeah. Unlimited. Yep.
So the question states that what's the probability that it takes 5 games until you lose? So the question is limited up to the number of trials. But then
That's only for this part though. That's only for this part where this part will say P of x is equal to 5, right?
that means, but if it says that it takes 5 games, that means it has to take 5.
It's asking, it doesn't say that it takes 5 games, it's asking what is the probability that you win at the 5th.
Yeah, so it thinks that because we're basing on those 5 games, the x value will be 1. But if the probability
I wouldn't say so.
it's not a
Probability of losing is
Because this question could have been anything. What's the probability that it takes 600 games?
yes, so would the value be 1
It's just the probability that you win at that trial, right? But the experiment itself can have unlimited trials. The values that it takes on are unlimited, right? Always a geometric distribution takes on unlimited trials. Unlimited number of the 5 games. This is just maybe I should have written this as part D, right? Yeah. So it doesn't confuse you. What's the probability of a success in this situation? And failure?
wait.
Wait.
The unlimited.
Yeah. And Q is 0.43. Yes, sir.
No, that's probability of losing.
Mm-hmm.
You said the probability of losing is P.
Read the question. How does this question end? Until you what? You lose. So that last trial in which you get the outcome that you need, that's the success. And in this experiment, until you lose is when you stop. Since that's when you stop, that's your success.
So the unlimited is very unlimited.
It is.
Because if you hit the target, then that's the limit.
That's the end, yeah.
So there's a limit.
But it means you could go on forever. Yeah. So what values can that x can take on any value, because x can be
Then,
Okay, if they told us, if they told
what is the probability that you will die today? It's a half. Does that mean that you will die today?
it's not a half,
It is a half, because you could die or live.
okay.
But does that mean that you will die today?
No, it doesn't.
See?
If they told us,
Hmm.
if that was the probability question, then they just told us, we take 5 games, so you lose.
Mhm.
Then you become 1
To
to 5.
5, yes.
That's what.
Yeah, you're right. Jeremy, are you filling in these things? Okay. All right, next one. You throw darts at a board. Does this make sense before we move on? Shannon, can you raise your hand if this makes sense? Cool. You throw darts at a board until you hit the center. Your probability of hitting the center is 0.17. You want to find the probability that it takes 8 throws. Now, this does not mean that there are only 8 throws. Yeah? Oh, dear.
No, like, you,
Yes, please explain.
just put this in your head. In this thing, in this part,
Geometric distribution.
the losing part is the goal. And then the losing, yeah,
Yeah.
according to
So losing is the success.
yes. Because you're aiming to lose.
Yeah.
So you plan to lose.
According to this question, you stop when you lose.
Okay.
You stop playing when you lose. Like losers say, I mean winners say, right? So when you lose, you stop playing. So since that's when you stopped, it's the success. Let's try this one. What values does x take on?
So when you stop the success,
Yes. When you
the
fail.
last value is the success.
What is the probability of a success in this situation? And a failure? How do you state the probability question? Thank you. I think you can do these ones. I just want us to go over this part. So you can try 2 and 3 on your own. If you have a question, you can ask me. Let's go over to this part. How do we notate, or what's the notation for geometric distribution? It's just what you see here. This x is a geometric distribution represented by g, and in brackets you have the probability of a success. So it's just as simple as that. Some factors about the geometric distribution. It also has a mean, a variance, and a standard deviation. The mean is, do I remember this? Let me be sure. Be sure. Yes, and we're going to do it on a curve. The mean is 1 out of p. The variance is that, and the standard deviation. Yes, p is the success. So yeah, fill out those formulas for mean, variance. You don't need to. You just need to write this last part for standard deviation. The last part, you don't have to write this. Just write the last part.
So, what's this other part? Oh, that's this.
Let me simplify it for you. Mean is it 1 out of p?
Yeah.
Variance is 1 minus p out of p squared. Okay? And that means standard deviation is the square root of variance. Simple as that. Okay, so Assume that a probability of a defective component is 0.02. Components are randomly selected, right? Let X be the number of components tested until the first defect is found. So what's the success in this situation? The probability of finding the first component, right? You stop when you find the first defective component. What values does X take on? This is always the same. Infinity. Write the probability distribution. Remember, it's written as X. So it's going to be 0 point. Yeah. Find the probability that the first defect is caused by the seventh component tested. Px is equal to 7. So, on your calculators, do you have calculators? Jeremy, would you please go get calculators? One of the small keys. So on your calculator, you go to Start. Yeah. Then you go to Calc. And then you go to Geometric PDF. You see Geometric PDF? You should say binomial. Where is it? No, sorry. You go to second and then distribution. Not start. Second distribution, second vars, VARS. Then you look for, where is it? Do you see geometric PDF? Geomet PDF? Geomet PDF. And then you put in so you click that. When you click that, it asks you for the probability of a success, which in this case is 0.02. And it also asks you for the X value, which is 7. So then that gives you the answer. So you put in 0.02, comma 7, then that gives you the answer. Okay. Yeah, so just to say this again, Shannon, you go to second function, then you push that button that says VARS, and then you look for geometric PDF, right? How many components do you expect to test until one is found to be defective? That's asking you for the mean. Mean is the same, yeah. Sorry? Thank you. Yeah. The mean is the same as the expected value. So what's the expected value here? 50. Effective. So before you find one defective component, you expect to test around 50 items. Did you see how to get it?
To get mean?
To get the first one. Geometry. Second, then you go to this button that says VARS.
Yeah.
Yeah. Then you look for geomet distribution. Geomet PDF. Can you try to finish the others on your own? Or are you going to need help? P 0.02, comma 7.
Wait,
Hi.
when I go to the X value, that's where I put
7.
the 7.
Yeah. Yeah, so that's the probability.
And then, okay.
So I don't see any question that requires us to find more than or less than, but it's the same idea as we did on the binomial distributions. If it had asked for at least 7, how would you get that? Or if it had asked for at most 7? For this same question, you guys are going to do the rest. But for this same question, if it had asked for at least 7, how would you calculate it? At least? Yeah, you're right. At least 7 would mean, yeah, which would be 1 minus 6. Okay? And then for that one, you would use cumulative distribution function. So you would use geometric CDF. Yeah. Explaining again. If it asks for at least 7, then you're looking for 7 and beyond, right? So you're looking for 7 included, and that's high. So you get the 1, right? And then you subtract these ones, which is less or equal to 6. Then for that one, you would use CDF, geometric CDF. Yeah. Yes. All right, try those other questions on the worksheet on your own. If you need help, let me know. Practice. I should have given you more homework.
At least, if they
I
are
thought
saying
this
at
would
least
take a
30.
while, but I already finished.
So when you're writing this,
It said at least 30.
yeah, it will be something like this, right?
Yes.
But then when you
Doing it,
yeah,
you
it
do
will
one.
be all the small ones and 29.
Yes. Absolutely. 29.
So in this question, I hope this is okay.
What did they do to you?
You have chemistry.
You have biology. You have statistics with them.
Oh, yeah. The very first number.
The last time, which one? How many components you expect to test? The last time which for developing cancer is 1 in 28, 1.2%. Let X be number of people you ask until once he or she has cancer. X is a discrete random variable with a geometric distribution. Or what is the probability that you ask 10 people before one says he or she? So that's just X equals 10.
10 because of the 10 people.
Yeah. So then you do the same on the calculator. Then you do it on the calculator.
Still that. Which, okay, how would I know that I'm supposed to use CDF or?
If it's just equals, you're using PDF. If it has less or greater,
If it has like, okay.
Yeah.
Okay.
So that's 1 out of 78. 1 out of 78 is the probability. Or 0.0128.
And then the value is 20 with 10.
Yep.
Wait, that would be for this.
Mhm.
9.4. Or
Yeah,
take
for this one. Yeah.
100. And then
When it says what's the probability that you must ask 20, does that mean less or equal to 20? Or does that mean? Hmm.
it's 20.
It can be more, it can be less. It has to be that.
But wait. Does it mean that the 20th person you ask has cancer, or does it mean?
You must ask 20 people. Means that there could be 4 people who have cancer. But you must ask 20 people.
Shouldn't that be less or equal?
No, because if you must ask 20 people, that means that no matter what the result is, you need to have the sample size of 20 people.
That means that if you had found someone with cancer at 10, you don't stop, you keep asking.
You keep going till you get to 20.
So it's less.
You keep going till you get to 20. So here, what matters is finishing. It's all about the number. It's like the result that matters.
Let me ask Google. By the way, do you know you said one matter?
One matter.
She said one matter.
I said one matter.
She said one matter. Yeah, he's a good player, man. He's a Manchester United player, so.
So that means
So it's equal to 20. It's
so
equal to 20.
don't I have to put that sign like this?
I'm also checking, but that's just equal to 20. One. If you say it so fast, it sounds like one. What? No. No. Say money. Bet money. I asked Google to pronounce one matter.
What were you doing?
Oh, it is better. Stupid, what's wrong with you? One.
See? One. Not Ruan.
One matter. One.
You're saying Ruan.
Do we have the correct pronunciation of your name?
It's not pronounced R.
It's
Bro.
not Javier, it's Javier.
Yes, thank you. Man, how did that even come up? Javier. What's it? Oh. Nope. Okay. I need to stop recording. Shannon, these guys are just working on their work, so yeah. Sorry about all the unnecessary banter.